Hi, my name is Cristiano Steffens. I'll be presenting a pipelined approach to deal with image distortion in computer vision. This work was done with my colleague Lucas Messias under the supervision of Professor Drills and Professor Botelho. Here, we extend a previous work published last year in which we show the impacts of image distortion in several image-based classifiers. For those who are unfamiliar with the image recognition classification task, please consider this as a classic approach to deal with garbage in, garbage out issue. Our models are only as good as our input data. If you have faulty data, you are likely to get unreliable results. Although images are multidimensional data, in which the content can be often inferred by the inherent relationship among distinct parts, we show that they are still susceptible to the same issues that we would find in doing tabulated data or on any classification and regression problems. So you have these outliers and all the problems that come with them. So image classification is a well-established problem in computer vision. Most state-of-the-art models rely on CNNs nowadays to achieve near-human performance in that task. However, many authors have shown that these CNN-based models are still susceptible to various image manipulation issues, which of course undermine the trustability in perception system. This is critical, especially when we consider unmanned systems, autonomous vehicles, and scenarios where light cannot be controlled. So we investigate the robustness of several deep learning-based image recognition models and how the accuracy is affected by the distortions. The distortions we have tried include IL exposure, low-range image sensors, and common noise types. Furthermore, we also propose and evaluate an image pipeline designed to minimize the image distortion before the image classification is performed. So, first, let us think about how an image can be affected at capture time. So some typical challenges when we are acquiring an image are high contrast, like when you are capturing a scene where you have a light source or a scene that's very contrasting. There is a very dark part and a very bright part in it. Think of it as taking a picture of the sunset. You either get the sun properly exposed or you get the rest of the scene properly exposed. Another typical challenge is low contrast. When you have an image or a scene that where its parts are not very distinctive. Or low light, when you have a weakly illuminated scene, like when you're taking a picture at night, taking a photo of the moon, or taking a photo of a party that in an environment that's not well illuminated. In order to compensate for those challenges, in order to get the best picture, we have a few options. First, we can change the lens aperture. A larger aperture equals more light getting to the sensor, and therefore you can use a shorter exposure time. However, a larger aperture also equals a lower depth of field, so you won't get a well-focused image depending on the other conditions. You can also change the exposure time, but a higher exposure time equals more blur. So if you have a moving object, if you have a dynamic scene, so you will get a lot of blur artifacts, which are not good. But a larger exposure time equals more light getting to the sensor, more time to convert light into electrical signals. Another thing you can do to get a better image in a challenging scene is to use more gain or less gain. More gain means more contrast, but it also means that you are amplifying noise. So, because both noise and the original signal are amplified. Furthermore, you also have problems with quantization, with sampling, with clipping, and all this is occurring while you're capturing the image and before you even get to store it. A few examples of noise include sensor defects, transmission issues, excessive gains, dead pixels, compression artifacts. And while a human may look at this and, well, they are the same picture, they have the same content, it's easy to see that. That's not true for a machine. So we are seeing the same content, but the picture is not the same. The way the data is represented is not the same. The same happens when you have misexposure, where you have images that are too dark or too bright. So in order to solve that, we came up with an idea that is a modular approach to maximize reuse. So we can use a model that has already been trained. There's no need to do retraining to acquire more data or anything like this. We can avoid model adjustment. We want to work in the standard RGB color space, so we are not interested in changing the acquisition itself, because there is a lot of different cameras and we are not interested in changing that. And we want it to be flexible to accept images in different image resolutions. So basically our idea is you have a scene, you get a picture of that scene in many different settings. You enhance that picture, you denoise it, and then you predict what its content should be. In order to test this approach, we have used some remarkable models which have achieved state-of-the-art performance in the ILS-RC challenge, which include the VGG, ResNet, Inception V3, Inception ResNet V2, MobileNet, DenseNet, NASNet, which was proposed in 2018. In order to do restoration, we have used the re-exposed edge for misexposed images. This model is based on a UNet and a content aggregation network, a CAN. It's provided as a one-size-fits-all, and it was adjusted on synthetic and real data. So it should be able to restore ill-adjusted, ill-exposed images in many different conditions. We also, for denoising, we have used CNN3, which is a very deep feed-forward CNN. It relies on the residual learning. It's appropriate for many denoising tasks as well as deep blocking. So for an overview of the results, we have this first column that shows the accuracy on the original images, and we have this set of tests that show the results for under and overexposed images, and further we have the denoising. So for mildly underexposed images where you still can see some data, like when using gamma equal 4, we see an expressive drop in the accuracy when we are not applying the restoration, but when applying the restoration, the accuracy comes close to what we would achieve over the original images. So none of the restoration or classification models was trained specifically to do this task. For gamma 6 and gamma 8, we notice a similar pattern. When for gamma 6 it gets worse, and even worse for gamma 8. But the restored images show a significant improvement. On gamma equal 1/4, we see that we also have a significant accuracy drop. NASNet Large, Inception ResNet V2, and Inception 3 are the best performing models, and MobileNet V2 is by large the worst performing model. When the restoration is applied, we see a significant improvement on the model's accuracy for all models. The same holds for Gamma 1/6 and 1/8. Now, when we get to the models affected by noise, for images affected by noise, the conditions are a little bit different. Here we see that for images affected by additive white Gaussian noise that is added to the input image and follows a normal distribution, the best performing models show results that are very close to the original to the results that are achieved on the original images, and the worst models like MobileNet V2, VGG16, and ResNet 50 show an expressive drop in accuracy. But on the restored images, on the other side, we see that for the best models, the restored images are actually worse than the damaged images. So here we have mixed results. We cannot be sure that we actually improved anything by using the restoration models. Also, for Poisson noise, we see that the best performing models are not very much affected by Poisson noise. They're pretty much the same. The results are pretty much equal. On the restored image, however, the results are much worse. Now we get to the two noise types that are signal independent, which provide the worst outcomes of all. Here, first we see salt and pepper, which is an impulse noise added by setting white or black pixels to the image, and it's often associated with dead pixels in the camera sensor array. And we see that we have an expressive drop in the accuracy, and the restoration makes it even worse. The same is true for speckle noise. The results get actually worse when we apply the restoration. Here, to summarize it, we see that we have highlighted low impact, moderate impact, and critical impact. Gamma 4 restored has low impact on all models. Gamma 1/4 quarter restored has a low impact on most models. Gamma 1/6 restored has a low impact on most models. Gamma 1/8 restored has a low impact on most models. Poisson has a low impact. The image with Poisson noise has a low impact on all models. The restored, however, worsens that condition, which is the same that we have shown before. And salt and pepper and speckle are critical in all conditions. The best performing model is reference 35, which is NASNet Large. So we have shown a comprehensive experiments on the robustness of state-of-the-art on CNN-based image recognition. We have tested several common image distortions, which include ill exposure, signal-dependent noise, signal-independent noise. We used a set of classifiers which had outstanding accuracy on the ILS VRC competition. We offer a succinct representation of the performance of the classifiers. We show that existing CNNs are little affected by slight misexposure or saturated pixel values. Poisson noise and additive white Gaussian noise have also a limited effect on the accuracy, but all models seem to be vulnerable to severe misexposure and signal-independent noise. In misexposure problems, we have shown that the restoration always improves the accuracy of the classification models. And next, we intend to do segmentation, mapping, and localization to see if these models follow the same robustness pattern. And that's all for today. If you have any questions regarding the experiments, or if you'd like to share your thoughts on these papers, please get in touch. Thank you for your attention.